Hello all, welcome back. In the previous two lectures we were talking about terminal velocity and thunderstorm cell model. Fall velocity or the terminal velocity is giving you an idea about the velocity with which the raindrop is falling. And after that we have seen the thunderstorm cell model. It is the model which is used for getting a knowledge about, getting an idea about the intensity of rainfall, intensity of precipitation actually. So, now it is time for us to have a look into numerical examples, so that you will get a feel of those terminologies. So, we can proceed to numerical problem solving. So, first example is on terminal velocity. First question, let me read it out. Raindrops of various sizes are carried by an air current moving vertically upward at 2 meters per second. Determine the velocity in meters per second of a 0.5 millimeter diameter raindrop. Also determine whether the drop is rising or falling. Assume density of water is equal to 998 kilogram per meter cube, air temperature 20 degrees Celsius. The coefficient of drag can be taken as 0.671 and air density 1.2 kilogram per meter cube. So, let us first see the data which are given to us, and in this problem we need to calculate the terminal velocity or the fall velocity of the raindrop. The wind velocity is given to you. Based on that we need to determine whether the drop is falling or rising. We have seen the mechanism happening within the cloud. So, in that some of the water vapor droplets are getting taken up and some are coming down, mixing up, all these processes taking place within the cloud. So, wind action is there, because of that lifting will be taking place, and due to condensation, when the water droplets are achieving certain diameter, it will fall down. So, let us check what will happen in this case. The data given are velocity of air current, that is the velocity of wind speed is given to us, that is 2 meters per second. Then diameter of raindrop is 0.5 millimeters, we are denoting it by capital letter D. Drag coefficient CD is 0.671. Air temperature is equal to 20 degrees Celsius, and density of water is 998 kilogram per meter cube. Air density is also given to us, that is 1.2 kilogram per meter cube. What we need to find is the terminal velocity of the raindrop, velocity with which it is falling, or we need to check, because we are having the wind velocity is given to us. So, we need to check whether the drop is falling or rising up. Let us start solving the example. Terminal velocity expression we have already derived. So, the same expression we will be making use here, and after that the given data we will be substituting in that particular expression. So, terminal velocity Vt is given by this expression, under root of 4 by 3 Gd by Cd rho W by rho A minus 1. In this we will substitute different values such as diameter of the droplet, coefficient of drag, density of water and density of air. After substituting, we will get the value, we can calculate the value as 2.85 meter per second. The velocity of the raindrop, which is calculated by using the equation for terminal velocity, is found out to be 2.85 meters per second. So, first part of the question is over. Now, second part we need to check whether it is rising or dropping down. The wind velocity is given as 2 meters per second. So, you can compare these two. The velocity of the current which is moving up is 2 meters per second, the velocity of the drop is 2.85 meter per second. Definitely here in this case the velocity of the drop is more, which is coming down. So, the raindrop is falling down. if the velocity is less than 2 meters per second, the velocity, terminal velocity which we have calculated is less than 2 meters per second, then the air current will be lifting up along with that. This raindrop will be lifted up by the air current. But in this case the velocity of the drop is more, so definitely it will be falling down. Now let us move on to the second example of thunderstorm cell model. Thunderstorm cell model, we have seen it is used for determining the intensity of precipitation. So, we have considered the thunderstorm cell slightly above of the ground surface. It was having an inlet region, uplift region and outflow region, and different atmospheric parameters needs to be calculated at different levels. After that we can get the how much is the intensity of precipitation which we are getting on the ground. This is mainly due to the convective lifting. That is why this cell was, thunderstorm cell was also termed as convective cell. So, both are same. If we are telling thunderstorm cell or convective cell, both are working under the same principle of convection, convective action. So, now let us see the question first. Determine the precipitation in centimeters per hour. You need to calculate the precipitation in centimeters per hour from a thunderstorm cell having 3 kilometer diameter with a cloud base of 700 meters and an average outflow elevation of 9.5 kilometers. The surface air temperature is 28 degrees Celsius, pressure 103 kilopascal with saturated air conditions, and wind speed is 2 meters per second. Assume a lapse rate of 6.5 degrees Celsius per kilometer. So, let us see the data again, data which are given to us. Based on that we need to calculate the intensity of precipitation. So, given data are storm cell diameter 3 kilometers is given to us. So, the thunderstorm cell, imagine the figure which we have drawn while deriving the expression corresponding to thunderstorm cell model. In that the diameter of the storm cell is 3 kilometers. Then cloud base depth, that is the cloud base is at a height of 700 meters from the ground surface. Then comes the average outflow elevation, that is at a elevation of 9.5 kilometers. Then air temperature is given as 28 degrees Celsius. Then air pressure is 103 kilopascal. Velocity of air current 2 meters per second. Lapse rate is given as 6.5 degrees Celsius per kilometers. Now, making use of these data, given data, we need to evaluate, estimate precipitation intensity in centimeters per hour. So, let us proceed to solve the example. So, this is the schematic representation of a thunderstorm cell. So, this we have seen already while deriving the equation for thunderstorm cell. So, we were having an inflow region and then it is water vapor is rising up and coming out through the outflow region, and due to condensation we are getting the precipitation which is having an intensity of I. The diameter is given to us as 3 kilometers and we have been given the cloud base is at an elevation of 700 meters. So, delta Z1 is 700 meters and it is mentioned that outflow region is approximately at an elevation of 9,500 meters. So, that is what is marked here. It is at an elevation of upper part of the uplift region is taken at an elevation of 9,500 meters. Here in the uplift region we are having the atmospheric parameters P1, V1, ρ1, QV1 and T1, and in the outflow region we are having the corresponding parameters P2, V2, ρ2, QV2 and T2. Now let us start solving the problem. Before that, let us see the expression for rainfall intensity. Intensity of precipitation or it can be rainfall, it can be of any kind of precipitation. So, it is given by the expression I is equal to 4 rho A1 V1 delta Z1 divided by rho WD multiplied by QV1 minus QV2 divided by 1 minus QV2. This equation we have already derived under the section of thunderstorm cell model. Now, here in this case, what are the things need to be calculated? We are having diameter of the cell, rho W we know, wind velocity we know, delta Z1 we know. We need to calculate the density of air, specific humidity at section 1, section 2. So, these values, air density, specific humidity, all these we have calculated with a numerical example while solving the examples related to atmospheric parameters. That is why I am not going to repeat it again, but let us see how these values are taken. So, the required values of atmospheric parameters are calculated at levels of 700 meters and 9500 meters, because our cloud base is at an elevation of 700 meters and the total elevation of the cloud upper part of the uplift region is 9500 meters. So, our section 2 is at 9500 meters and section 1 is at 700 meters. So, we have been given the values corresponding to atmospheric parameters near the ground surface. According to the ground condition, what are the temperature, pressure, these values have been given. Now, we need to calculate the corresponding values at 700 meters and also 9500 meters, 9.5 kilometers. What are the parameters to be calculated? Temperature. How can we compute temperature at a higher elevation? We can make use of the Labstrate equation. So, temperature can be calculated by this familiar Labstrate equation, T2 is equal to T1 minus alpha, Z2 minus Z1. Now, second is the atmospheric pressure. Atmospheric pressure at the ground level is given to us. Now, we need to calculate the corresponding value at 700 meters and also 9500 meters. This can be calculated by using this formula which we have derived while seeing the relationship between the pressure at higher elevation and lower elevation, or the variation of pressure as the altitude increases. We have seen this equation. This is based on the principle of hydrostatic law and also the ideal gas law. So, this can be utilized for calculating the pressure at different levels. Third one is air density. Air density from the ideal gas law we can calculate as rho A is equal to P by rho RAT. Next is we need to have the idea about vapor pressure. Vapor pressure E is required for calculating specific humidity. So, vapor pressure calculation we will be doing by making use of the empirical equation for saturation vapor pressure. We know the temperature and corresponding to the temperature, that is ground level temperature we know. At different levels we can calculate the temperature, corresponding to those temperature we can calculate the vapor pressure. After that we need to calculate specific humidity. The equation for calculating specific humidity is given by QV1 is equal to 0.622 E by P. The values which are known to us is at the ground level, that is 0, we are taking Z is equal to 0 meter, and then cloud base is at 700 meters and the uplift region is extending up to 9500 meters. So, the values at the ground level are known to us, that is the temperature is 28 degrees Celsius and the same value is converted into Kelvin, it will be 301 Kelvin, because some of the expressions are derived based on ideal gas law, then temperature should be substituted in Kelvin. Corresponding values for 700, Z is equal to 700 meters, we are calculating. This has been calculated by using Excel spreadsheet. It is coming out to be 23.45 and minus 33.75. Now, for calculation point of view, for the calculation of air pressure, we know the expression, we need to calculate T2 by T1 to the power of G by Ra alpha. So, for that separate columns have been made and we have calculated air pressure at ground level is given to us, and we will be calculating at the level of 700 meters and 9500 meters. Now, air density, we have seen the expression from the ideal gas law we can calculate. So, that has been calculated as these values. Now, what we are going to do, we are having section 1 and section 2. So, uplift region, outflow region. This way our thunderstorm cell is schematized. So, in that we need to have the values corresponding to specific humidity, air density, all at section 1 we were representing. But at section 1 it is varying from 0 to cloud basis up to 700 meters. So, what we will do, we will take the average value of these values corresponding to air density and specific humidity corresponding to 0th level, that is the ground level, and at an elevation of 700 meters. That is the values of QV1 and rho A1 corresponding to section 1. We will be averaging out the corresponding values between 0 and 700 meters. So, that is why we are having a separate column for rho A bar, average value of ground level and 700 meters. These two have been taken, that is 1.15 as rho A1, and then so this is rho A1. Now, vapor pressure can be calculated by the empirical formula. So, ground level 700 meters, 1500 meters calculated to be calculated with as these values. Now, specific humidity is calculated 0.622 E by P. So, E is known to us, P is known to us. So, specific humidity can be calculated. In the similar way as we have done for rho A1, we are doing it for QV1 also, that is we are averaging out the values at ground surface and also at an elevation of 700 meters. So, QV1 is calculated to be 0.021. Now, we need to calculate the intensity in meter per second. What we are going to do? We are going to substitute here in this particular expression and we will get the corresponding values. So, intensity of precipitation is given by this expression and we are going to substitute for the corresponding values. Rho A1 you can see it is taken as 1.15. That 1.15 we obtain by taking the average value corresponding to the ground level and at the cloud base. Uplift region, we are having only one elevation, that is at 9500 meters, that value is considered. So, the rho A1 is taken as 1.15, V1 is given to you air wind velocity, that is 2 meter per second, and our delta Z1 is 700 meters. Rho W we know 1000 kilogram per meter cube and diameter of the cell is 3000 meters. Now, again QV1, coming to QV1 is average of the QV at ground level and the cloud base. So, that 0.021 is substituted here and QV2 is taken as the value which is calculated for 9500 meters, that is 0.0007 divided by 1 minus QV2, that is 1 minus 0.0007. That can be calculated as 4.36 into 10 to the power of minus 5 meters per second. But in the question it is specifically mentioned that the intensity I should be calculated in centimeters per hour. So, when we convert that into centimeters per hour, we will get a value of intensity of precipitation as 16 centimeters per hour. So, this way we can calculate if the atmospheric parameters at the ground level is known to us, we can make use of those values and we can calculate the corresponding values at upper levels, upper elevations. Those equations we have derived. By making use of those equations, we will be calculating different atmospheric parameters such as temperature, pressure, then comes the specific humidity, vapor pressure, all these air density, all these things can be calculated by using the known expressions. After that, by making use of the equation for intensity of precipitation, by making use of the convective cell equation or the thunderstorm cell equation, we can calculate how much is the intensity of rainfall or intensity of precipitation which is experienced on the ground surface. This is the procedure behind that. So, in this while doing the solving the numerical examples, we have seen two problems. One is related to terminal velocity, that is a very simple problem, just substitution of the values only. Second one is the thunderstorm cell model. So, for doing this problem thunderstorm cell model, we need to calculate various atmospheric parameters. After calculating that, we have substituted in the equation and we got the final result. So, here I am stopping today's lecture. Thank you.